Jennifer Wilson again. She's going to continue about with her talk about Steinberg modules of SLNZ. Give it away.
Great, thank you, Peter. So maybe I will begin with a bit of review of what we covered last day and remind us all of the notation. So again, I'm going to use R to denote the ring of integers in a number field, which I'll call F. Okay. And so recall that we have the result of virtual Beery-Ekman duality. Which says that if I'm interested in computing the rational cohomology of my special linear group with entries in R in codimension I, well, this is the same as the degree I homology of SLNR with coefficients in this rationalized Steinberg module, okay, where let's recall what the Steinberg module is. So our dualizing module here is the Steinberg module. It is defined to be the top homology, I've run out of space, top homology of the Teats building associated to the field F. So here, the Teats building is the geometric realization of the poset of proper non-zero subspaces of F to the n under inclusion. So here, remember our vertices correspond to subspaces. In Fn, and our simplices correspond to flags. Okay. And so the theorem of Solomon and Teats that this Teats building is homotopy equivalent to a wedge of spheres in dimension n-2. And moreover, that our top degree homology is generated by apartment classes. Where an apartment is indexed by a frame for F to the n, that is a decomposition into lines. And the apartment corresponding to that frame is the full subcomplex of the Teats building. That is on vertices that correspond to direct sums of these lines. Great. And so, right, it was in an exercise from maybe even more than one of these classes to verify that these apartments are spheres of dimension n-2. Okay. So last time we discussed this theorem of Ash and Rudolph, which states that if R is Euclidean, then we can say something stronger. Then this top degree homology group is generated by integral apartment classes. Oops. All right. So by this, I mean classes, these apartment classes where if I look at the intersection of each of these lines with Rn, then that direct sum is equal to Rn. So in other words, these are apartment classes where the frame arises from not only a basis for f to the n, but in fact a basis for r to the n. Okay. And so in our talk last time, the main goal of the talk was a proof that we could use this Ash-Rudolph theorem on generation by integral apartment classes to prove a theorem of Lee and Sharba, where the theorem of Lee and Sharba was on the vanishing of the top dimensional cohomology, pardon me, of SL and R rational coefficients when R is a Euclidean ring. Okay. And maybe I'll pause here. So this is our review from last day. Let me pause in case there are questions before I continue. Okay, great. Well, in that case, we can move on to today's goal. So today, the goal is a simplified proof of this theorem of Ash and Rudolph due to Church, Farb, and Putman. Okay, great. So in order to proceed with this proof, maybe I'll start a new slide. Jeremy can forward to the next page, slide 6. Let us review some simplicial methods, some terminology around simplicial complexes. Okay, so this is, first definition is probably familiar. If I have a simplicial complex X, and I have a simplex sigma, so let's say sigma is spanned by vertices S0 up to SP. Okay, the link of sigma in X is by definition the subcomplex on simplices of the form T0 up to TQ, such that S0 up to SP and then T0 up to TQ is a simplex in X. Great. So, so let's see a picture just to remind us. Maybe here's a picture of X, and here is my sigma, and maybe let's say this is a solid triangle here. Okay, so how do I compute the link? Well, I look at sigma, I look at all of the simplices that contain sigma, and then I take the subsimplex opposite sigma in that simplex. So here, the link is going to be, in this case, the union of this line and this pair of vertices. Okay, great. That's a link. And with that, we can make the following definition. If X is a d-dimensional simplicial complex, then we say that X is Cohen-Macaulay or CM for short, if two conditions are satisfied. So the first condition is that X is d-1 connected. So it's as connected as a wedge sum of spheres of dimension d. And the links in X have to be similarly as highly connected as wedges of spheres. So for every simplex sigma, the link has to be d-2 minus dimension of sigma connected. Okay, so some examples of simplicial complexes with this property. If you take, for example, the standard simplicial structure on a ball or a sphere, or you take the barycentric subdivisions, then these are going to be Cohen-Macaulay complexes. So exercise, check that. And then maybe in contrast, here's a picture of a simplex that is not Cohen-Macaulay. So let's look at the link. This simplex here. So here's another exercise. This complex is not Cohen-Macaulay. It's the link of this point of this vertex is disconnected, which is a problem. Okay. So great. So having stated this definition, let's talk about an example of a Cohen-Macaulay complex and how we will use its Cohen-Macaulayness to prove our goal, ask Rudolph. So let's define the complex of partial bases. Okay. So in the following, again, let's fix R to be a Euclidean ring. And F to be its field of fractions. Doesn't need to be a number field. Okay. And here's a definition that a subset V0 up to VP in Rn is a partial basis if it's a subset of a basis. Possibly equal to a basis, does not need to be a proper subset. Okay, so here's a couple warm-up exercises along these lines. Verify that if I have a single element, V0 in R to the n, then this is a partial basis if and only if it is primitive. So what that means is, by definition, that means the components, the ideal generated by the components of the vector V0 generates R. Okay. So I claim that V0 can be extended to a basis if and only if this condition holds. And another exercise is to check the following. Here are examples of some vectors in z to the 3. And I claim these are not partial bases. So I claim there is no way to extend these pairs to bases. Okay, leave those as exercises. And now we can state the definition, the complex of partial bases. Okay, so complex of partial bases. Great, the vertices of this complex are primitive vectors in Rn. And the simplices are partial bases. Okay, great. And in fact, this is, I would maybe prefer, instead of thinking about this simplicial complex, to think about its barycentric subdivision. So, so maybe I'll make this remark that the barycentric subdivision of this complex well, in that case, my vertices are now going to correspond to partial bases. So the barycentric subdivision of this complex is going to be the realization, the geometric realization of the poset of partial bases under inclusion. Okay. Great. I'm going to go on to slide 7 and state a theorem of Mason from 1979 is that when R is Euclidean, the barycentric subdivision of this complex of partial bases is Cohen-Macaulay. Okay. So great. So you can check this. This complex is n-1 dimensional, and this says it's as highly connected as a wedge of n-1 dimensional spheres. Okay, great. And so our goal to proving this Ash-Rudolph theorem is going to be to relate this this complex of partial bases, or its barycentric subdivision, to the Teats building, and use that to get a nice generating set, an integral generating set for the top homology group. And the key to doing that in this proof is going to be the following key lemma, which is due to Quillen. And to state this lemma, I'm going to use the following notation. So if X is a poset, then I'm going to write X, these bars, to denote the geometric realization. Okay, and so here is the lemma. Okay, the lemma says, if I have a map, f from x to y, of posets, the map of posets, and in fact, a strictly increasing map of posets, subject to the following conditions, or given the following. So if y is Cohen-Macaulay of dimension d, and additionally, the fibers of this map are nice in the following sense, that for all y in my codomain, if I look at this subposet of x, that's this sometimes referred to as the fiber, though it's more than just the preimage. It's the poset beneath the preimage. Okay, if for every y, this subposet of x is also Cohen-Macaulay, then the conclusion is that X is Cohen-Macaulay, and importantly for our purposes, it will imply that if I look at the map induced by F on the top homology of the geometric realizations, then this map is surjective. Okay, great. And right, I'm not going to prove this lemma. It is one of the bonus exercises on the handout to prove this lemma. And the key is to use a spectral sequence that Quillen developed associated to this map of posets. Okay. Great. So these are the ingredients that we'll need for this proof of Ash-Rudolph. So remember, the goal is to prove that the top homology of the Teats building is generated by integral apartment classes. Okay. So here's what we'll do. We're going to use the lemma with the following posets. I'm going to take Y to be the poset of proper non-zero summands of f to the n. Okay, and so notably, the geometric realization of Y is going to be exactly our Teats building, and it is dimension n-2. Okay. And X is going to be the poset of proper partial bases. So partial bases that are strictly smaller in cardinality than a basis. Proper partial bases, non-empty, of Rn under inclusion. Okay, so then the geometric realization of X again is the barycentric subdivision of the n-2 skeleton of the complex of partial bases. Okay, and now we can define our map F from X to Y just by taking spans. So I take a partial basis of R to the n, and I take its span over the field F. Great, okay, and so our goal is to apply the lemma and then use surjectivity of this map in top homology to prove our theorem. So we've got two things left to do. One is we need to actually check the hypotheses of the lemma to make sure it applies. And then we need to work out why it is the case that surjectivity of this map completes the proof for us. Okay, so let's check the hypotheses of the lemma. Of Quillen's lemma. So I will leave it is not hard to check that the map F is strictly increasing. If I have strict containment of bases, then I will have strict containment of their spans. Okay, very good. So let's check the next condition, which is that if I look at any subspace V, any proper non-zero subspace V in Fn, then this set we've defined, F sub V, okay, it's an exercise to check that this set is going to be precisely the subcomplex on partial bases contained in V. Okay, and so that is going to be exactly the barycentric subdivision of this partial basis complex of V, and that is Cohen-Macaulay by Mason's result. Okay, golden. So we've checked the hypotheses of the lemma, and that means that Quillen's lemma now implies that we get this surjective map great, from the top homology of this n-2 skeleton of our partial basis complex to the top homology of the Teats building. Great. And so now we need to show that this map, this surjectivity, gives us generation by integral apartment classes. So let me draw a picture. Okay, so here's a picture in the case n equals 3. And here is, so here's a picture. If I take a partial basis, v1, v2, v3, then we'll finish writing that in. So this is a partial basis, v1, v2, v3. Then in this complex X, well, maybe I'll put it this way. In the partial basis complex, there is a top dimensional simplex, in this case, a 2 simplex corresponding to that partial basis. But we are in the n-2 skeleton of this partial basis complex. So here, this simplex is missing. There's the missing simplex that would correspond to this basis v1, v2, v3. Okay, and so if I take the boundary of this missing simplex, that's a sphere. And if we look at what our map does, what the map, what this map does, well, it arises from this map that takes spans. So this is going to map the boundary of this simplex precisely to the apartment in the Teats building I get by taking the lines spanned by these basis elements. And I won't finish writing in all the sides of the triangle, but this is what we get. We get the apartment corresponding to QB1 plus QB2 plus QB3. I guess I'm also working over Z and Q in this example. And this is looking promising because this is going to be precisely an integral apartment. This is an apartment that arises from a basis, a Z basis for Z to the 3. Great. And so we're almost done. I guess our instinct might be that because the partial basis complex was n-2 connected, then maybe the n-2 skeleton of this complex has homology generated by the boundaries of all these deleted simplices. If that were the case, we'd be done. And that is the case. And so let's verify that. And then this will conclude our result that the homology group is generated by the images of the boundaries of these deleted simplices, and those images are exactly the integral apartment classes. Okay, so let's check this fact. Okay, so consider the pair. In fact, let's consider the long exact sequence of the pair of this partial basis complex relative its n-2 skeleton of strict partial bases, proper partial bases. What that tells us is that we get an exact sequence the following form. Okay, but fortunately, this term is 0 by Mason's result on the connectivity of the partial basis complex. And so we get a surjective map here. And so, great. So what does that give us? Well, when we combine this surjective map with this surjective map, we get a composite, the following composite. Okay, so, oops, supposed to be surjection. So here, this surjection is by Quillen's lemma. This surjection is by this exactness of the sequence. Okay, but great, this group, we understand this group, because X is exactly the kind of codimension 1 skeleton of this partial basis complex. This homology group is going to be exactly the group of n-1 chains on the partial basis complex. So this group here, this is n-1 chains on our partial basis complex. But those n-1 chains, those are exactly, that's exactly the free abelian group on bases for R to the n. Okay. And so that's great. That's exactly what we wanted. We are now done. We have this surjection from these boundaries of missing simplices to our onto our apartments that generates homology, and we can conclude that we are generated by integral apartment classes. Okay. So we're done. Our conclusion, I'm now on slide 8, and just writing the conclusion that this top homology group is generated by integral apartment classes. Okay, when R is Euclidean. Great. And so that proof, that was the main proof of the talk. But I guess I have a little bit of time left. So why don't we talk about Mason's result and how we can prove that this partial basis complex is Cohen-Macaulay. All right, and we'll focus on the case when n equals 2. And so the first thing to check, it's an exercise to check, that to prove Cohen-Macaulayness in the n equals 2 case, it suffices to show that, excuse me, this partial basis complex is a connected graph. Oh, and because it's enough to show it's a connected graph, I guess it doesn't matter whether we work with the version that's barycentrically subdivided or not. Connectivity is equivalent. Suffices to show that this partial basis complex is a connected graph. Okay. And so let's think about this. Let's choose a primitive element. That means that A and B are coprime. And our goal is to build a path to 1, 0. I guess I'm doing this now, maybe in the case when R is a number ring, so it contains a copy of the integers. Oh, actually, I don't need that. No, I think we can do this for any Euclidean ring. Okay. The claim then is that we can use the Euclidean algorithm to build an edge from our primitive vector AB to a primitive vector CD, with D strictly less than B with respect to the Euclidean norm function. Okay, and once we've done that, we are done by induction. Then we can just continue iterating this procedure until we get this second term down to 0. Okay, and so here's how we can do this. Okay, if we choose any basis, any completion of the primitive vector AB to a basis, and it's an exercise that's possible. So that's that earlier exercise that this condition of being primitive is equivalent to the statement that I can complete this vector to a basis. Okay, so we'll choose any basis. And then the Euclidean algorithm, the definition of a Euclidean ring and its Euclidean norm tells us that there exists some number Q and R with the property that when I look at this difference, D prime minus Q times B, that is going to be strictly less than B. And so then we can define our new vector CD to be this difference, this linear combination. Okay, and it's an exercise that is not difficult to check that that AB and this new vector CD still form a basis. And at that point, we are done. And so that proves the claim. And with the claim, again, we can iterate this until D is 0, and then we're done. So this is a proof of the of Mason's result in the case that n equals 2. We've shown this graph is connected. Great. So I have even a little bit of time left. And so that's what I wanted to.
Question by Kai Uwe.
Oh, there's a question. Yes. What's the question?
So this proof looks as though it's actually proving that like SL2 over that ring is generated by elementary matrices.
That is a related statement. I agree.
That is a related statement.
Absolutely.
Is there a, so if I look at cases n greater than 2, and then I would expect like cohomologiness that is better and better connectivity. So that would translate into finite presentability and stuff. So is there also a related algebraic statement about nice ways of generating SLN are very nice ways by elementary matrices? Do the higher cases of Mason's lemma also relate?
That's a great question. And I agree. It does seem like that should be the case. And I don't know what precisely to say.
If you like being a fancy higher categorical person, then this is used to, you can put all of the GLNs together as like maybe I shouldn't say this, but like there's instead of like viewing the groups and like constructing presentations of that, there's ways of rephrasing it in terms of like you form you take all of the GLNs together and view that as a ring, and then it's about like syzygies of that, or like causalness of that ring and things like that. But that's sort of a different direction. But I think there are, so basically I don't know of any like nice concrete descriptions, but they're sort of, once you buy into algebraic jargon, there are interpretations of higher connectivity for higher n, but it's not as concrete, at least that I'm aware of.
Well, thanks.
So I'm happy to take more questions. If there's time after the questions, I was hoping to take a couple minutes to point out some of the exercises on my exercise sheet, since in my opinion, some of them are fun. And so I wanted to give a teaser for some of those, but maybe
so
first
Jenny,
we should take questions.
Jenny, if you're done with your talk, well, let's just thank you for your talk right now.
Okay.
And then we talk about your exercises.
Sure.
Are there more general questions about this talk? Andrea? Yeah. Let's go with Andrea first and Tara second.
Okay. So what can one say without the hypothesis that the ring is Euclidean? Are there counterexamples?
Yeah, that was the first lecture.
Yeah, that's right. That's right. So definitely, if the ring is not a PID, then you are not generated by integral apartment classes. That's Church Barb Putman proved something stronger than that. That came up in the first lecture. And so the question is a question for number rings that are PIDs but not Euclidean. And there was some work I did with Jeremy and Peter and Don Yasaki, where we showed that for the known collection of quadratic number rings that are that are PIDs but not Euclidean, that this generation by integral apartment classes fails in that case. And this result did in fact use questions about whether SL2R is generated by elementary matrices.
In particular, also the ring with -19 was included in that it's not generated by integral apartments, even though the top cohomology, we couldn't show that it was non-zero.
That's right. Oh, and it's known to be 0 in one case, I guess, too, which is
It's known to be 0 for n equals 2. Yeah.
So that's it. So I guess that I think Dan Margalit asked me whether generation by integral apartments was possibly equivalent to vanishing of that top dimensional cohomology group, and the answer is no, because we know of that one number ring and n equals 2 where it vanishes, alas.
Great. Tara, did you have a question? No, okay, you put yourself on unmute, that's why I was assuming you had a question. Maybe anybody else with a question?
Maybe a slightly different. You're saying, so this vanishing of Euclidean domain, does it also hold for local field, or it's just a global field?
I will repeat the question, I assume. Did you hear it?
I did not. Please repeat.
So the question was whether whether you can do this for local fields or only for Euclidean domains.
Yeah,
Sorry.
So in the case of local fields, then your ring of integers is always a DVR, which is a Euclidean domain. So I was wondering, this vanishing also holds for that as well. Can you hear me?
I don't think she can.
Okay,
The question was if you have a local ring, then the ring of integers is always a DVR and automatically a Euclidean domain, and whether the results hold in that situation as well. Did I repeat it correctly this time? No, still not. The problem is that she showed it for all. She showed it for all Euclidean domains. It doesn't really depend on the field.
So maybe you can hear me now. Sorry.
No. The proof was only for Euclidean domains.
Yeah. So the vanishing is for Euclidean domains, but I was wondering if it's only for the ring of integers of a global field, or does it also hold for ring of integers of local field, because that's Euclidean domain anyway, right? So.
That's right. So this generation by integral apartments, these results are just for any Euclidean ring, and then F the field of fractions. So it does not need to come from a number ring inside the number field.
Yeah.
So the integral apartments is for any Euclidean ring, and that will mean that the homology with coefficients in Steinberg is automatically vanishes, but you don't have Borel-Serre duality, so you don't get anything for like top dimensional cohomology if you look at local fields.
Okay, I see. Okay.
Yeah, sorry, I heard local rings and not local fields. My bad. I was a little tired. Sorry about that. Another question. Well, if there's no more question, let's thank Jenny again.
Oh, great. And can I still claim these last 3 minutes to preview exercises?
Talk about some exercises.
Yeah. Great. Can I, or maybe I can enlist Jeremy to do that. Maybe that's easier. Jeremy, could you change your screen from sharing the Jamboard to sharing the exercises? Or maybe I should do this. Maybe it's easier if I do this. Just need to figure out.
Probably it's easier if you do it. I stop sharing.
Okay.
So then hopefully you can share.
Are we looking at my exercises now?
Yeah.
I think. Okay, excellent. Oh yeah, great. So the exercises in here fell into a few subcategories. There is the first section are I guess, some warm-up exercises on the nature of summands of R to the n, where R is a PID. So that those are good exercises. But let's see here. So more directly related to the talk, the first exercise sequence is on the technical definition of what it means for something to be a building. And the goal is to guide you through the steps of verifying that the Teats buildings are in fact buildings. And so there are a few things to check to verify that. The first is to check that every apartment is isomorphic simplicity to a Coxeter complex. So there's a definition of that, and you can verify that this, well, we talked about how these apartments look like barycentrically subdivided boundaries of simplices. And so you can understand why that is in fact the Coxeter complex associated to the symmetric groups. And from there are some conditions to check on relationships between different apartments. And so there are exercises, there are some hints for those exercises. And it involves doing a little bit of linear algebra to look at the relationship between different flags. In fact, I think the most challenging part of this exercise is you need to check that if you are given two different flags for f to the n, where f is some field, then you need to be able to produce a basis or a frame that is compatible with both of those flags, in the sense that you can write all the subspaces in both of those flags as spans of subsets of the basis. And so I think that is the most challenging step in this exercise, in my opinion. And it's sort of cool. It's just, in a sense, elementary linear algebra, but I think it's not completely trivial. So that's an exercise to do. The next exercise sequence is on a proof of the Solomon-Teats theorem. So this is the theorem that the Teats building is homotopy equivalent to a wedge of spheres. And the key to this proof, or at least this is a proof that I learned from notes by Mladen Besvina. The key to this proof is a tool that's sometimes called discrete Morse theory, or PL Morse theory. And the idea is we're going to build up the complex inductively by starting with something that's contractible and then adding on additional vertices and coning off each new vertex that we add in such a way that we have at every stage in this construction either something that's contractible or something that is homotopy equivalent to a wedge of spheres. And so that, I think, is both a good exercise because the Solomon-Teats theorem is a significant result, but it's also a good exercise because this discrete Morse theory lemma is something that I think is quite useful, and it's a good tool to have in your tool bag. So it's a good application of this kind of general construction. Okay. The next exercise sequence is on constructing the Sharbley resolution, which is this resolution of the Steinberg module that was originally constructed by Lee and Sharba in their proof that the co-invariants vanish when R is a Euclidean ring. And right, this is also essentially an exercise in working with simplicial complexes. The key to their construction is this so-called acyclic covering lemma, which is that if you have a CW complex X that is a union of subcomplexes, so you cover it by these subcomplexes X of A, with the property that all the intersections and the intersection of any collection of these subcomplexes is acyclic, then the homology of X is isomorphic to the homology of the nerve of that collection of subcomplexes. Okay, so that acyclic covering lemma, that's the key. And then the the argument is I think, quite nice argument by Dudley and Sharba in considering appropriate covers of the Teats building and of related complexes that they define. Okay, so you're guided through that exercise. Great, aha. Oh, and here is exercises pertaining to the Ash-Rudolph theorem. That I think these relate more directly to, these might be a repeat of results that we proved together in the lectures. Great, and then finally the exercises for today's lecture are all, I think, asking you to rework the results that we proved together in lecture. Plus, if you're feeling ambitious, to prove Quillen's lemma on maps of cosets. Okay, so oh dear, now I've gone over time. But anyways, thank you. So I think these exercises are cool, and I think some of them are illustrative of useful techniques. So I wanted to give that pitch.
Well, thank you so much, Jenny, for putting all this work into preparing those exercises for us.
It was fun.